Alright, let's talk about compilation of C into assembly language. So we know C, from CSE 121, maybe you've taken 224 and so on. C is a high-level language. It lets us write statements that are pretty close to what we actually want to do. If we want to compute, square root of b squared minus 4ac, we can say sqrt parentheses b times b minus 4 times a times c, close paren, and it will figure out how to make that happen. Now, a processor like our PIC processor doesn't know about square roots, division, multiplication. It knows simple multiplication. So, as usual, to do one thing, like execute this one arithmetic expression, might take a lot of assembly language instructions. And so, rather than having to write that assembly language ourselves, we work in high-level language like C. And we use what's called a compiler. Compilers convert that C code into assembly language, right? These low-level instructions that we've been using all quarter on our PIC processor. So what does this look like? If we want to do this by hand, we can do that, but it's interesting tool that does this compilation for us. And what you're going to discover is that a typical compiler does not do as good a job as you could probably do by hand in trying to compile code. So if you hop into your browser, and in the problem set there's a link for the XC8 compiler from MPLab, and that link probably takes you to this page, view downloads. And so you have a set of download options. If you're running Windows or OS X, you can use these downloads. For Linux, I would use this download, and it's going to download a file which is, you can see on the bottom here, xc8 blah 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 .run. So I've already done that download so that we don't have to spend time waiting for it. And on Linux, the way that I'm going to install this xc8, I'm going to make it executable, and then I'm going to say sudo /xc8, and this will run it as a super user. And it's a pretty straightforward installation. Let me just show you the options that you'll see. So go ahead and accept the license agreement. We're going to do the free version, which is not a very sophisticated compiler, but it's free. So we'll just leave that at free and say next. I'll leave the default installation. I'm going to put in both of these. I don't know if they matter or not, but we want this compiler to work with MPLab X. So I'm going to go ahead and check both of those settings. And then say next, and this will take about a minute to go through the installation. And then after it's finished, we're going to go ahead and run MPLab, and I'll show you how to set this up. So meanwhile, let's look at what we're going to compile. So I've just written a stub of a main program, something that has a running loop. So we'll initialize a running sum to 0, and then inside a loop we'll keep adding our loop increment to the sum. And then we'll do some arithmetic. We'll set x, y, and z to some values, and we'll change sum to be x times y plus z. And then we'll do a conditional statement. If sum's bigger than 100, y equals 4, else y equals 5. And then we'll go ahead and add that to sum. And that's going to be our whole program. Doesn't do anything in particular, but we'll compile this and see how the compiler does in coming up with PIC assembly language instructions to do these operations. So our installation is just about done. There we go. Okay, so if you want to use the free compiler, click next. We're going to click next. And then we can say finish, and we're done. So I can close this out, and now I'm going to run MPLab. And so you're going to get to do this in your homework problem set. You're going to install a C compiler in your installation of MPLab and play around with compilation. see what it does. So this is our usual IDE, and I'm going to say File, New Project, and I'm going to call this C-test. I'm just going to say Next. I'm going to put in PIC18F1220. And then we'll stick with the simulator. We're not going to actually simulate this, but I'll tell it it's a simulator anyway. And then it will bring up the tool chains, and we should have a new option here for XC8. So if we want to do assembly language, you're going to pick this one. If we want to do C programming, we'll pick this one and say Next. And I'll call this C-test 270. And I'm going to say set this as the main project, and I'm going to leave everything else the same, and I'll go ahead and say finish. Alright, so I've got my project up here, C-test 270. I'm going to go under source files. I'm going to right click and say new and say C main file. And I'll just call it main. And I'll just go ahead and say finish, leave everything else default. And so when I do that, it generates a little bit of code for me. It's got, you know, a header block in the beginning. It's got our sort of typical includes that we want. Here's the prototype for our main program, the beginning of our main program, and here's the end of our main program where it returns with a value of success. So let me go ahead and grab all of this code, and let me paste it into here. So there's my C program, and we want to go ahead and compile it. So I'll just hit the hammer symbol, and it'll run, and it compiles. And we can take a look at our data here. Program space use 196 of 1,000 hex bytes, so about 5% of our program memory, 7.5% of our data space. That's our file registers. Alright, so what did it do? Well, we can go to Window and Debugging Output and ask for a disassembly listing, and we have to do this change to our properties that we always need to do. So I'll go to Project, Properties, and come down here to Loading, and we're just going to check this symbol. And we'll say OK. And then we'll rebuild it. And suddenly we have our disassembly listing pop up. Alright, so let's take a look at this. This has got some interesting things to it. First of all, it's got comments in it, right? Even MPLab knows the value of writing good comments. It's showing us how it's going to do multiplication. So this is a multiply routine that it is writing for us, and it says a 16-bit multiply can be decomposed into 3 8-bit multiplies, right? A, B, C, D, those are each 8-bit numbers, so we have to do B times D, and then we have to do A times D and B times C. And then we would do A times C, but we're only producing a 16-bit sum, so we don't really care about A times C. So we produce these 3 things, and then we add them together, and that gives us our 16-bit number. And then here's the assembly language code for actually doing the multiplication, and it uses this multiply, W by file register, do 8-bit multiplication, and it does that 3 times. So all of this down to here, this is a multiply routine that's being supplied for us. So when you write a C program, for example, if you say printf, you don't tell it how to print things, right? You just say printf. It gets the code that makes up the printf function from somewhere. Well, this got the code that makes up a multiply function from somewhere. Alright, so here's the beginning of our actual program, and it says integer sum equals 0, and that corresponds to these 4 instructions. Well, what's happening here? It's putting a 0 into W and putting that into file register 11, and then a 0 into W and putting that into file register sum. Well, where is sum? We can look at the binary for this instruction and see that sum must be file register 10. So with that in mind, we can start to try to create a memory map. And let me see if we can do that. And I do not have a document camera handy, so let me go ahead and open up a window. So it's putting sum at locations 10 and 11 hex. And then we say for I equals 0, I less than 10, I plus plus. So what does this do? Well, it takes a 0 and it puts it into location 13, and then it takes a 0 and puts it into location I, which is file register 12. So I is location 13 and location 12. So, you know, when you write a program in assembly language, you've got to use a variable. For a timing loop, you have to decide what file register is that going to be. Well, the compiler makes those same decisions. It decided sum's going to be stored at locations 10 and 11, I is 12 and 13. Why is it 2 locations? Because integers in this version of C are 16 bits. And a file register is only 8 bits, so it uses a pair of file registers to store each of these integers. Alright, so now I want to do sum equals sum plus I. So what does this do? It takes I and it moves it into the W register, so I is location 12, puts it into the W register, and then it takes the file register called sum, which is location 10, and it adds that to the W register. And then it takes the W register and stores it back into sum. Alright, so what does that mean? It's taking the least significant byte of sum and the least significant byte of I, adding them together, putting them back into the least significant byte of sum. So it's adding those low 8 bits. And then it does the same thing, but it uses locations 13 and 11. That's the high byte of sum and the high byte of I. And those get added together, but notice what it does. It does an add with carry, which means if adding those low bytes produced an overflow, it's going to add one more when it adds those high bytes. It's doing that carry from the 8th bit to the 9th bit. So all of this is accomplishing sum equals sum plus I, but it's doing a 16-bit addition instead of an 8. And so we can see that location 10 is the least significant byte, 11 is the most significant byte. So we can label those locations accordingly. And then it's going to do some funny stuff down here. It's got to complete this for loop, right? So it's done the sum equals sum plus I. Now what does it need to do? It needs to increment I, see if it's less than 10, and if it is, go back and repeat this for loop. So it increments file register I, that's register 10, so that says I equals I plus 1, and it says skip if it's not 0. So if I was equal to 2 and we increment it, it's going to be equal to 3, that's not 0, it's going to skip this. But if I was equal to 255 and we incremented it, that increment would leave the 0-bit set, so it would not skip this instruction, and in that case it would increment file register 13, which is the upper part of I. So these two instructions together achieve a 16-bit increment. First we increment the low byte, and then if that turns out to be equal to 0, we add 1 to the upper byte. Alright, and then it tests bit 7 of file register 13. That's the upper byte of I. Okay, skip if clear bit 7. Why is it testing bit 7 of the file register? Well, bit 7 is the sign bit, right? And so when you take a 16-bit number, that least significant bit, bit 7 of this, most significant bit of this most significant byte, if that's a 1, you have a negative number. So it's checking to see if this is equal to 1. Why is it doing that? Well, our condition we're checking for is I is less than 10. So the first thing it does is it says, is I negative? Because if I is negative, it's guaranteed less than 10. So we test bit 7, and we say skip the next instruction if it's clear. If it's set, if our number I is negative, we're going to execute this instruction, which says go to 13A. And when we go to 13A, what does it say? It says go to 112, and what's 112? That's where we do I sum equals sum plus I. So if I is negative, we're going to go back up here, we're going to repeat our sum equals sum plus I, the body of our loop. But if that bit 7 turned out to be clear, I is not negative. So we're not going to do this go to instruction. And instead, we're going to come down here, we're going to move that most significant byte of I into the W register. And if it's not 0, we're going to come down to location 13E. Okay, what does it mean if that most significant byte of I is not 0? It means I is bigger than 255. So it's not less than 10, so we're going to leave our for loop and come down to 13E, which is the beginning of our next chunk of code. Otherwise, what do we know? I is not negative. I is not bigger than 255. So now we need to see if that lower byte of I is less than 10. So it puts a 10 in the W register. It subtracts I from the W register. And then bitdist file skip if set status 0. So this is a way to do a conditional branch instruction. So what is bit 0 of the status register? Well, let's take a look at our special function registers. Now let's see if we can find status. Status right there. Bit 0 is the carry bit. Alright, so this is saying if the carry bit, after we do that subtraction, is set, then we should skip this instruction. If it's set, it means that I is not less than 10. So we skip this, we go to 13E, and we're out of our loop. Otherwise, we go to 13A, and 13A takes us back to 112, and 112 begins the body of the loop again. Alright, so this is not the way you or I would write these instructions in assembly language. This is a very long-winded approach. You and I know that I is never going to be anything other than 0 through 9, or 10. So we could get away with an 8-bit value. We know it's not going to go negative, right? There's lots of things we could do. We could initialize it to 10 and count down, and then do a branch if not 0. And that would be a lot easier than doing all of this funny business. But the compiler doesn't have that insight. At least the free compiler doesn't. So it has to follow a very algorithmic, mechanical approach to coming up with this assembly language code. Nonetheless, if we go ahead and we assemble this and we run it through the simulator, it will do exactly what we think our C program should do. So you can look at this. I'm not going to go through the rest of this in detail, but for example, here we've got x, y, and z, and we set x equal to 12. So what's happening here? X equals 12, y equals 520, and z equals 1000. So it looks like y is file register E, that's 14, and so F is the upper part of Y. So Y is in those locations, E and D. Sorry, that's going to be F and E. And so this instruction here, put a 2 into file register F. That's setting this upper byte of Y. And then put an 8 into file register 14. That's the lower part. So what's the value being put in Y? It's the hex number 208. Right? So this upper byte looks like the number 2, and this looks like the number 8. So what does that turn out to be in decimal? This is 256 times 2 plus 8, which is 512 plus 8, which is equal to 520 decimal. So this set of 4 instructions here is setting Y equal to 520. Now we said set X equal to 12, but we don't do anything with that, right? X is not actually being initialized with a value here. So Z is equal to 1000, same thing. We put a 3 into the upper byte of Z, and then E8 into the lower byte, and if you add up 256 times 3 plus this number, you should end up with 1000. Alright, and then sum equals X times Y plus Z. I don't know why X equals 12 is not being performed up here. That's interesting. But now it's going to do X times Y plus Z. And so it's going to put a 0 into W, put that into, so it's decided to do X equals 12 down here. So it puts a 0 into the upper byte of X, and then it puts a C into the lower byte of X. And why does it do that? Well, because it's supposed to do X times Y, and it's going to use the value of X as one of the arguments to this multiplication routine, and so it's setting X equal to 12 here so that it has access to that information in the W register. So we won't go through the details of this call, but calling something basically involves saving your operands somewhere and then doing a call to the multiply routine, which in our case is at location 192. So if you go up here at location 192, that's where the multiply code starts. And then the multiply code saves the result somewhere, and we take that result and we move it, in this case, into something that we use to add Z, and then put it back into sum. And then here's another conditional if sum is bigger than 1000, and you can see how this works. And again, sum is stored at locations 10 and 11 hex. So it looks at location 11 and it does something with location 10. And the result of all of this is if sum is bigger than 1000, it should end up right here. Otherwise, it's going to end up down here in this Y equals 5 part. Alright, so that's an example of compilation, and you know, we've got 194 lines of assembly language. Now some of these are comments, some of these are macro definitions, and some of this is the multiply routine. But the multiply routine, you know, takes about 81 lines of code, and then another 100 some lines for this relatively simple C program. And one more thing to look at, we noticed that at the end here, you know, we had our if statement. If sum's bigger than 100, set Y equal to 4, otherwise set Y equal to 5. But it didn't actually generate any code here for Y equals 4, Y equals 5. Why not? Well, it's doing a little bit of optimization. It knows that once we give Y a value, we don't do anything with it. So let's just go ahead and do something down here, sum equals sum plus Y, and see if we can trick it into actually setting Y equal to 4 or 5. So we'll recompile, we'll come back here, and so sure enough, here's our if sum is bigger than 100. And if we get through all of this calculation, we find out that it is, we should set y equal to 4. Well, y is at file registers F and E, so it takes a 0, puts it into file register F, and then it takes a 4 and it puts it into file register E. That sets y equal to 4, and then it goes to 19E, which does this sum equals sum plus y. Otherwise, it's going to say go to 19E. Otherwise it's going to say y equals 5. So if it turns out that sum is not bigger than 100, it will execute this go to 196, which comes down here. It will execute this go to 196, which is right here. And that says put a 0 into the upper byte of y, and then put a 5 into the lower byte of y, and that sets y equal to 5. So you can use this tool to play around. You can make code, you can see what it does, you can modify the code, see how it changes the assembly language, and start to get a better feel for how this compilation process works. It's pretty remarkable that, with a relatively simple processor that can support, a few thousand bytes of instructions, 256 bytes of data, that we can take C programs that include things like, multiplication, and actually compile them and have them fit on the processor. And we've taken 5.5% of the program space on this little PIC chip. So this is a fun thing to play around with. It's also fun to think about how you would write something like this, right? How would you make a program that takes this and turns it into that? And if you're computer science, you go to university, you can take something like, a compiler design course and actually dig into how something like this works. All right, that's all we got for C compilation. Thanks.